Welcome to the Explainer. Okay, I am absolutely thrilled to get into this material with you today. We are venturing right into the physics, and specifically the thermodynamics of human consciousness. Now, I know that sounds like a heavy lift, but we're going to break down some incredibly groundbreaking research that is literally shifting how we look at the brain. We're moving away from these rigid, static models and getting into dynamic, flowing continuums. It's going to be a fun ride.
So here's our roadmap for today. We're going to tackle the paradox of order, explore the neural continuum, and unpack the thermodynamic brain. After that, we'll figure out how to actually measure dynamic consciousness, and finally, we'll draw up a cartography of the mind. Let's jump right in.
All right, Section 1, the paradox of order. Now, when you and I think of order in a physics sense, our minds usually jump straight to things that are neat, highly symmetrical, and perfectly structured, right? But as we're going to see in a second, physical order definitely does not always mean complexity. To really hit this nail on the head, I want to throw a slightly weird, counterintuitive question your way. Is a crystal conscious? Well, no, intuitively we know it's not. But why exactly? If you look at classical physics, a crystal has an insanely high order parameter. Its atoms are perfectly aligned, the symmetry is totally rock solid, and structurally it's pretty much flawless. Honestly, if consciousness was just about perfect, rigid physical order, a crystal would be the smartest thing in the room.
And that right there is the paradox. While a crystal is incredibly ordered on a physical level, it has zero dynamic regulatory complexity. It just sits there. Now compare that to a living brain. The brain is this messy, flowing, highly adaptable network. It thrives on what scientists call multi-scale regulation and oscillatory diversity. So the order of the human mind isn't about being perfectly rigid or flawless. It's all about having organized, dynamic control. It's moving. It's reacting.
Moving on to Section 2, the neural continuum. So how exactly does the brain organize all of this messy, flowing, non-stop activity? Well, to figure that out, we need to look at something called the Brain Kinematics Model, or the BKM for short.
The BIKM brings us this really fascinating concept known as neural strain. Picture a viscoelastic network in your head, kind of like a memory foam mattress, but built entirely out of neural pathways. Whenever a sensory input or a new experience hits your brain, it acts as a stressor. And these stressors literally, dynamically deform those neural pathways. Some of that deformation bounces back to normal immediately, but some of it actually sticks around and gets consolidated into a memory. That physical and functional deformation, that is exactly what we mean by neural strain.
But neural strain isn't the whole shebang. Strain is actually just one single variable in a much larger, flowing picture that we call the neural continuum. Think about fluid dynamics for a second. Pressure is a super important variable, sure, but pressure isn't the fluid itself, right? In the exact same way, the neural continuum is made up of all these interacting mechanical fields, electrochemical activity, electromagnetic forces, and memory structures, all flowing together at once. Strain is just one piece that helps shape that massive dynamic pattern.
Okay, that brings us to Section 3, the thermodynamic brain. So what's the actual physical engine that keeps this entire continuum flowing? To answer that, we have to pivot over to the incredibly cool thermodynamic framework put together by Gustavo Deco and Deco Kringelbach.
And here is the absolutely crucial takeaway from their work. The brain never reaches equilibrium. Let that sink in. In classical thermodynamics, a system at total equilibrium is a system where absolutely nothing changes. And in biology, well, equilibrium basically means you're dead. A living, conscious brain is constantly pulling in energy, processing information, and dissipating heat to maintain what's called a non-equilibrium steady state. This non-stop energetic flow is the exact engine that gives us the ability to adapt, to learn, and to be creative.
Deco and Kringelbach's computational models actually map out the brain's different dynamical regimes, and it's fascinating. You have an integrated state which has super high global coordination, but the downside is that too much integration kills your flexibility. Think of what happens during a seizure. Then you have a segregated state which is great for specialized processing but terrible for global communication across the brain. And then you have the critical state. This is the absolute sweet spot. It's flexible, yet it's stable. Most neuroscientists now believe that healthy, everyday waking consciousness happens right here, perfectly balanced on the edge of this critical boundary.
What I absolutely love about this research is how perfectly these two models, the Deco-Kringelbach framework and the BKM, actually complement each other. On one hand, Deco and Kringelbach are speaking the language of thermodynamics,
They're talking about entropy, probabilities, and state transitions. On the other hand, the Brain Kinematics Model is speaking pure mechanics, strain flow, viscoelasticity, and continuum trajectories. But here's the magic. They are basically just two different mathematical languages that are beautifully describing the exact same conscious flow, which perfectly sets up Section 4, measuring dynamic consciousness. If consciousness really is this flowing, non-equilibrium, multi-scale continuum, how on earth do we actually measure it? Like, what's the metric?
Well, since we already established that a traditional order parameter would falsely tell us a static crystal is more conscious than a human brain, researchers had to come up with a totally new metric. Enter the Continuum Organization Parameter, or the COP. This changes the game completely. We are no longer looking for rigid, static structural regularity. Instead, we are measuring the degree of organized dynamic regulation happening within that biological continuum.
So the COP formula is built on 4 main pillars. First up is coordination, which we can actually measure by looking at EEG coherence. Second is oscillatory diversity, which basically means spectral richness. Third is adaptability, measured by the brain's flexibility to smoothly transition between different states. And finally, memory depth, which we can see in the persistence of functional networks. When you put all 4 of these variables together, coordination, diversity, adaptability, and memory, you get an incredibly accurate picture of the continuum's real regulatory capacity.
Let's zoom in on that second pillar, oscillatory diversity, just for a second. Think back to our crystal. A crystal has practically 0 collective modes of internal motion. But your brain? Your brain is a literal symphony. It's got these overlapping delta, theta, alpha, beta, and gamma rhythms, all interacting with these deep thalamocortical loops. The greater that coordinated diversity is, the higher the overall continuum organization. A dynamically pulsing, rhythmic brain ranks infinitely higher on the COP scale because it's seamlessly weaving multiple timescales and adaptive feedback loops into one cohesive, conscious experience. All right, let's head into our 5th and final section to see how this translates into real-world science, a cartography of mind. How do we actually map out this thermodynamic landscape?
Using this model, we can basically look at all biological life through a brand new hierarchy of organization. Down at level 0, you just have raw matter, like our rock or our crystal. Sure, there's physical order, but 0 adaptive regulation. As we climb the ladder, we hit level 1 with basic living cells, then level 2 with the distributed control we see in plants. Level 3 brings us nervous systems and vertebrates. By level 4, the continuum has developed enough to handle self-modeling and memory. And then at the absolute peak, level 5, we have highly focused consciousness. Think of a moment of brilliant creative insight or deep reasoning. That's where the continuum is achieving both extreme integration and extreme flexibility at the exact same time.
Now, here is why this matters. This model completely reframes how we understand different brain states. Through this lens, deep sleep isn't some disordered or broken state. It's simply a low conscious order state on the continuum. REM sleep is an intermediate, internally organized state. And things like seizures or anesthesia, they aren't just your brain's off switches. They actually represent a sort of pathological rigidity where that crucial adaptive order is lost, even if the brain waves look highly synchronized on a monitor. Every state you experience is just occupying a different spot on this dynamic continuum.
Of course, to take this from theory into strict, measurable scientific reality, researchers have a pretty massive roadmap ahead of them. First, they have to mathematically define those continuum variables and coupling laws. Then, they need to develop the transport equations, construct a preliminary COP metric, and then ruthlessly test that metric across all sorts of brain states, from deep meditation to full-blown seizures, using hard empirical data from EEGs and fMRIs. It's a rigorous step-by-step process to essentially build a thermometer for consciousness.
Now, you might be wondering, why does all this high-level physics actually matter to you and me? Well, it's a game changer because shifting a brain's thermodynamic landscape could literally revolutionize medicine. If we can map these physical thermodynamic dynamics directly to subjective human experience, we open up entirely new ways to understand depression, to map out schizophrenia, and to treat disorders of consciousness. We could use it to precisely guide brain stimulation or medication. We could even measure the literal physical effects that things like behavioral therapy and meditation have on the flow of the mind.
And that brings us right to the core breakthrough of all this research. The idea that consciousness depends not on maximal order, but on maximal organized adaptability. Our minds simply are not built on rigid, perfect symmetry. They are built on a messy, beautifully flowing flexibility that allows us to navigate a world that is constantly, unpredictably changing.
Which leaves me with one final thought I want you to chew on as we wrap up today's explainer. Right now, as you process the information we just went over, your brain is actively dissipating energy. It's aggressively maintaining its non-equilibrium steady state, and it's coordinating an absolute symphony of diverse oscillations just to focus your attention on my words. So, what exactly is the organizational state of your neural continuum right now? Think about it. Thank you so much for joining me to explore this incredible thermodynamic miracle. Keep learning, keep questioning, and I will see you in the next explainer.